Okay, so this question here is a question about radioactivity from P8. It covers a lot of different skills. This one here is one that you would find on a higher paper. So, this here, a nucleus of lanthanum 140 is a radioactive isotope. So, lanthanum is the element, 140 is the isotope. It has a mass of 140. So, it emits gamma radiation. What happens to the mass number and the charge of the nucleus when gamma radiation is emitted? So, the answer is nothing happens. Gamma radiation is electromagnetic radiation. It has no charge and it has no mass, so it can't change anything about the nucleus. So it stays the same. This is just a recall question. It's one that you just have to know. Now, B, why is it difficult to detect gamma radiation? So this is a recall question that you have to link your knowledge of how Geiger counters work to the properties of gamma radiation. So Geiger counters work by detecting ionization events. Gamma radiation is weakly ionizing. I apologize for my handwriting, but it is weakly ionizing. Okay, that means that it's going to pass right through the detector most of the time. Okay, so gamma radiation is weakly ionizing. Activity is the rate at which radioactive source decays. A teacher measured the count rate from a sample of lanthanum 140 using a Geiger-Müller tube. Explain why the count rate was less than the activity of a sample of 140. So count rate and activity are very different. Okay, the reason that it was very difficult to detect this was basically because of the fact that activity emits in all directions in 300 and it's three-dimensional. Okay, or actually, how am I going to phrase it? I'm going to phrase this as radioactive decay sends gamma rays in all, and I bet you that's going to be an important word, directions. The detector only measures I'm going to actually rephrase this. I'm going to say it only measures a small cross-section of the area. Okay, if I draw a two-dimensional picture, basically, if I've got my source, okay, the radiation is going in every single direction, basically an expanding sphere like this, and my detector is only right here. So it's only going to measure the gamma rays that come from that direction there. It's not going to measure all the rest of this. Okay, so that's what I'm trying to get across with my answer. So, yeah. So I would expect you're going to need 1 mark for that it extends it off in every direction. You're probably going to get 1 mark for saying that the activity, or that the counter only sees some of it. Okay. So why did the teacher stand as far away as possible? Okay, so this is just about safety now. Here, a teacher is doing a show how it can pass through some lead, okay, which gamma rays can. So why does the teacher stand as far away as possible? It's all about reducing the exposure to radiation, and why they do that because radiation increases cancer risk. So you want to limit your exposure as much as possible. Okay, so radiation has a dramatic decrease the farther away you are, and you just want to have as minimum risk as possible. So here are the results. Okay. The teacher concluded the count rate was not inversely proportional to the thickness of the lead. Explain why the teacher was correct. Use the data in the table below. So, inversely proportional. So we have to know what inversely proportional means. Inversely proportional means that X is proportional, or actually I'm going to go the other way around, that Y is proportional to 1 over X, okay? What this would lead to is that if you had 1/2 of, or if you double X, I'm going to rephrase that. So 2 times X would equal 1/2 of Y, okay? So if we look here, so we're going to use data from the table to show why. It is not inversely proportional. So a couple of ways that we can do this. If it is inversely proportional, then this column times this column should be a constant. Or we can look at it like this. And we're going to look at it like this. So going from 0.5 to 1.0. So if it was inversely proportional, then if thickness doubles, then count rate should have. Okay, so we look at going from 0.5 to 1.0. What we get is that 60 divided by 110 is equal to 0.54. Which does not equal 0.5. So it should equal 1/2, 0.5. Okay. All right, the other way that I can look at it is if I go, let's pick 2 other values here, these ones here. I can go 1.5 times 33. And that equals 49.5. And 2.0 times 18 equals 36. And 49.5 does not equal 36. So there has to be an understanding of how you're figuring this out and what inversely proportional means, and a mathematical way to prove that it isn't. both of these ways are valid. You don't have to do both of them. You would still get credit for the answer. So what they would be looking for is an acknowledgement of the method that you're using. Okay, so if you're using the half method, you get a mark basically for the statement and a mark for figuring out what is doubling the thickness and then proving that it's not halving the radiation. Okay, so that is that part of the question. Okay, lanthanum-140 can also emit beta radiation and change into cerium. Complete the equation showing the decay of lanthanum-140 into cerium. So, a beta radiation is an electron. An electron has a mass of 0. So the top number is the mass number. And it has a charge of -1. Okay, now the secret is that on both sides of this arrow, numbers at the top have to add together to stay the same, and same thing with numbers at the bottom. So 140 minus 0 is still 140. And 57 minus -1 is 58. Okay, so you don't need a periodic table for this. This is how you figure it out. So the -1. So this here is having to have a knowledge of what an electron is and how to do these kinds of nuclear equations. And here we go, a half-life equation, where it looks like we're looking at the half-life or half-life graph, or decay graph, really, that you could use to figure out half-life using the number of atoms and time. Okay, so different isotopes have different half-lives. The half-life of an isotope can be found by studying how the number of atoms changes over time. True. So, use data from figure 2 to determine the ratio of the number of cerium atoms to the sample when it was 100 seconds old compared to when it was 350 seconds old. So we have to look here. Right, so this here, 4 marks, this is kind of annoying. So what we have to do is we have to look at finding what the half-life is. Okay, so to find the half-life, we start at 5, so we go to 2.5, because that's when it will be halved. And that's right here, and I'm willing to bet that's 50 seconds. Just because the math is going to work out. So, my half-life is 50 seconds. So I have to look at how many half-lives does it go through. So, T 1/2 is 50 seconds. 350 seconds minus 100 is 250 seconds. 250 divided by 50 is 5. Five half-lives. So, what is the ratio? So 1 half-life is 1/2, and it's going through 5 of them. So 1/2 to the power of 5. 2 to the power of 5. And that is equal to 1 over 32. So the ratio is 1. Well, actually, they're going to want it the other way around, aren't they? Because the bigger number's got to go first. 32 to 1. Okay, so it started out, for every 32 atoms that there are now only 1. So in between 100 to 350 seconds, that is what happens. Okay. Determine the activity of the sample when the second was, or when it was 200 or 20 seconds old. Okay, this is a really tricky and high level question. Okay, because it takes a real understanding of what activity means. So this is a very high order question. It's one of the few places where you're expected to know what a tangent is. Okay, so we have to look at what does activity mean, and activity is the change in atoms divided by the change in time. And for that, you have to be able to take a gradient. But this is a curve and doesn't have a gradient. So what you would have to do is draw a gradient. I'm going to really struggle with this because I'm on my iPad here. I'll do my best. But a gradient is a straight line that only touches the curve at one point. That's not too bad. At the time that we're looking for. So the time is at 20 seconds. So a tangent is a line that only touches the graph in one spot. And then what I need to do is calculate a gradient from that. So the gradient is, we go across, like this. This is probably really exciting viewing. And a vertical line, you want your gradient. You can pick values that are pretty close and valuable, or that are convenient for you. So what I need to do to calculate my gradient is a change in y divided by a change in x. So here I have, we're going to call that 4.5. And this is 2.7. Okay, so my change in y is going to be 4.5 minus 2.7. Or I got to go the other way around. It is y2 minus y1. So 2.7. Oh, it doesn't matter because I'm gonna be taking an absolute value of it anyway. Okay, and my change in time, each of these are 2 seconds. So that's 3. So that is 6 seconds. And this, I'm going to go with 39 seconds. So my change in x is 39 minus 6. So I'm going to take those values, and I'm going to go here. So you get marks for actually drawing your tangent on the graph and trying to take a gradient. So with my values, 2.7 minus 4.5. And I don't want to forget this is times 10 to the 23, because that is right here. And then divided by 39 minus 6. And activity is always a positive number, so I'm going to take the absolute value of that, because I'm going to get a negative value if I do that, and that actually doesn't make physical sense. So 2.7 minus 4.7 to the 23 minus 4.5 to the 23. And then I'm going to divide that by 33. And that gives me a value of 5.5 when I round it. 5.5 times 10 to the 21 becquerels. And just quickly looking at the mark scheme, that falls within the range. With this one here, because drawing a tangent is particularly tricky, and you can draw it multiple ways, there'll be a range of answers that you can get. Okay? And you must, you've just got to, even if you get stuff wrong, if you draw your tangent properly, you can get 1 mark. And actually taking your values and using a gradient, okay, will give you a mark as well.